Excellent. Well, thanks a lot for the opportunity. I'm going to be presenting on the behalf of a very large collaboration. Let's hope I don't fumble this up. There are significant parallels between CMB-S4 and the Cosmoglobe in the way that they both merge expertise and knowledge from a number of different experiments. I'm going to very briefly cover the experiment design here, and then I have some interesting tidbits about the data analysis stacked up for the end. In its full shape, CMB-S4 will field about over 500,000 polarization sensitive bolometers on 2 ground observing sites spread across a number of different telescopes, both high resolution and low resolution. And big part of the design is that it relies on demonstrated technologies. In satellite speak, we rely on a high technical readiness level. Rather than fielding something experimental and in the hopes that it will work, what we are planning putting together will work because it has been done before, and we are just doing things at the industrial scale. We will field 2 large aperture 6-meter dish telescopes in the Chile Atacama site, allowing us a wide field of view, seeing up to 70% of the sky from the Chilean observing site with these high resolution telescopes. And we will field 1 5-meter telescope for delensing purposes on the South Pole site, and 6 low resolution large aperture telescopes with tons of detectors for observing the primary CMB field. The reason for the South Pole site is the case for the South Pole site is very easy to make. From the South Pole, you can observe the same field on the sky continuously. It never sets. It's always above the horizon if you find it above the horizon at any given time. And that allows you to focus all of your integration time on a very limited field on the sky, just pushing down the noise up until you see your primary science signal in there. And this is not possible from the Chilean site, even if it were drier, because close to the equator, your primary field will be below the horizon or below the optimal observing elevation for extended periods of time. But the congruence of the 2 different sites is really where the best gains are there to be had. The point of fielding this large aperture telescope also on the South Pole, the high resolution telescope, then allows us to perform precise, deep observations of the lensing signal in the same field as the deep CMB observations are performed. And a very novel feature of the S4 design is that these small aperture telescopes being fielded on the South Pole site can be refitted with a half-wave plate and redeployed in the Chilean site should there be a detection of the primordial B modes, one of the primary science cases of CMB stage 4. Now, it'll take a while to put this all together. The 7-year survey is currently projected to start in 2031. So we're talking about matters in sort of a distant future, especially for considering the timescale typical ground experiments. I have included 2 slides with more precise technical specifications of the small aperture and the large aperture telescopes, including the frequency coverage and the resolution. There's no point in going into the detail, but these slides will be offered. On the right are illustrations of the footprint of the small aperture telescope field focal plane on the sky. And the one thing that should be committed to memory is that the field of view of the small aperture telescope is about 30 degrees across. And when you point a telescope with a 30-degree field of view on a narrow field that you intend to observe ad infinitum, the center of the field will be continuously observed no matter how the bore side travels across the field. So this allows you continuous integration over your primary science field as long as you have the telescope on sky. And there are essentially, in the current design, there will be two configurations, either the split CMB bands plus high frequency optics tubes, or split CMB bands plus the low frequency optics tubes. And an important feature of the design is that these optics tubes that are co-located on the same mount are actually also co-positioned. So you will have different optics tubes, different fields of view, all co-positioned and overlapping, allowing for deeper integration of that primary field. If you just took the total number of detectors and made sure that none of them were looking at the same field, you would have a much wider field of view and you wouldn't be able to focus that integration time. The LATs in the current design have 85, these are the large aperture high resolution telescopes, will in the current design have 85 distinct optics tubes, each housing dichroic bolometers and allowing for these high resolution observations over a 8-degree field of view at any given time. The scan strategies will differ dramatically between the Chilean sites observed with the in our jargon, SLAT, and the South Pole Large Aperture Telescope here. Our measurement requirements are well motivated and are designed to yield the science requirements, or comply with the science requirements set forth in our design. Our four primary science goals are the primordial gravitational waves, ineffective, and then SZ-based cluster catalogs, and also transient science with the gamma ray bursts. And these measurement requirements are laid out as transfer function deconvolved noise and noise power spectra, noise biases of the full 7-year season maps for the small aperture telescopes here on the top, for the large aperture telescope at the South Pole here in the middle, and finally the large aperture telescopes on the Chilean site, observing a very wide field of the sky of approximately 68%. CMB-S4 is unique in many ways, but at the same time, aspects of CMB-S4 are already present in the stage 3 experiments. And I wanted to point out that these parallels between the Cosmoglobe effort and CMB-S4, the project comes from the idea that we can't continue to grow and reach higher sensitivities by performing these experiments in vacuum, but instead in 2013 the CMB community decided that we needed to pool our resources to field an experiment that would exceed the sensitivities and detector counts of all the past experiments. In 2031 we plan to have more detectors on the sky under the auspices of CMB stage 4 than all the current operating stage 3 experiments combined by an order of magnitude. And that obviously requires the expertise of both of the major US funding agencies, the Department of Energy and the National Science Foundation. And that means that this needs to be a whole different project than we've typically seen in CMB field. Failure is not an option for a project of this scale. That means a lot tighter review schedule, but also a lot better characterized and motivated measures of success. We know what needs to be done to field a successful experiment, and we can meet all those, and we know what it takes to meet all those requirements. And those are continuously inspected, examined, and refined as the project goes on. There was a specific question given to the presenters today about the data analysis challenges, and here are a few that immediately rose to mind. One of them is the sheer data volume. If you field an order of magnitude more detectors than has been done before, it is the equivalent of drinking out of a fire hydrant. These data rates are perfectly compatible with early stages of the LHC data throughput, with a very different data processing requirements following that. And the sheer volume of data may limit the available data reduction methods. We may not be able to reduce the entire data set, even at a single frequency, because it just does not fit memory on any available machine. And that then may necessitate batch processing and filter and bin approximations, where you make the decision to produce a biased maps at the expense of certain science goals. And the other challenge is that these science goals are ineffective. So the clusters and the transients may also compete against one another in what is the optimal way to reduce data, and may require several independent pipelines, which is a big deal to support when the data set volume is what it is. Another question offered as guidance to the presenters was to talk about the systematics, and these were already discussed at length in the previous talks, and S4 will have the same systematics in many ways as currently operating stage 3 experiments. But one of the things that we're most concerned about is anything that is scan synchronous and time dependent. Filters do a great job in rejecting, say, ground pickup and other scan synchronous signals if they're not time dependent. You can build a template, you can project it out, and you're done with it. But say that the rising sun over Chile produces a glare off the ground that you pick up with your telescope, and it changes as the sun travels along along its trajectory. Then that filter that would have been perfectly successful in capturing stationary signals actually leaves a significant residual that you then have to contend with. If the experiment is halfway plate modulated, a lot of the systematics are suppressed, but then halfway plate synchronous signal equally will contaminate your data and needs to be treated with. And I've listed atmosphere here because it is our big adversary in analyzing data from the ground. The question to which degree it will complicate data analysis for polarization is an open question, especially at the sensitivities that we're pushing for. We certainly know it to dominate everything in temperature and across all angular scales. All flavors of detector mismatch lead to parasitic signals in the pair difference time streams, and will need to be treated. And finally, optical system will always have tricks up its sleeve that need to be addressed. Both what happens in the main beam, especially for beam scale science like the clusters, and also what happens at the far side lobes, and especially the polarized response that the experiment will have on galaxy and also ground pickup due to the far side lobe structures. And on the right, I have an illustration of the extensive baffling and shielding currently in the design to limit many of these scan synchronous signals already before we even begin our data reduction. I don't have a plot of what a typical segment of time motor data will look like for CMB stage 4, in part because it'll look different for different telescopes and different observing sites, but also because it will look very similar to what Sigurd already presented and what I know to be coming in as a part of the Simons Observatory presentation a little later on. But we know that the intensity signal will be dominated by atmosphere with neat frequencies up to 1 or even tens of hertz. And a lot of that atmospheric fluctuation cancels in the pair differencing, where you take two polarization orthogonal bolometers and take the difference to measure the polarization modulation of the sky. And that pair difference signal is our primary primary polarization signal that we then attempt to reduce into maps. And it will have low frequency 1/f style noise that can be decomposed into three different sources. You have the instrumental 1/f that you would have even if you had a dark bolometer. There will be unpolarized atmospheric and another unpolarized 1/f signal that comes from the detector mismatch, be that calibration, bandpass, or other sources. And finally, the big uncertainty is the extent of atmospheric polarization signal that the differencing cannot resolve and will have to be mitigated at the map making stage. For main challenges, I want to highlight some. For example, we've never fielded this many detectors. So going from the current scale of fabrication of detectors to the magnitude that needs to be reached for S4 is a challenge, but we're early in the game and we have good idea of how that exactly will be achieved by deploying several fabrication facilities with individual expertise in different things, and then coming together, harmonizing the production process and applying industry standards to quality assurance and such things. Typical stage 3 experiment reports an observing efficiency of about 20% over the entire season. That means that out of 365 days of the year and out of your entire array of detectors, the integrated detector hours that you could have been observing your primary field drops to about 1/5 of the optimal observing efficiency. And that has been perfectly acceptable up until this point. And because this is the demonstrated achieved observing efficiency, it is what we're using as the basis of our forecasting. And there are some frequency specific factors that go into that as well. But if we can realize a better observing efficiency, that will also mean that we're able to realize much better sensitivities and achieve depths. Sheer data volume is obviously going to be a challenge, and we have good ideas on how we will address that in the data reduction side. And at the same time, time is our friend. And after two another deployments of NERSC supercomputers, we expect there to be enough computing capacity to meet the requirements of stage 4 data reduction. And there will also be unknown unknowns that come with the extreme sensitivity that we're aiming for. So that is something you have to plan for. And with this, I've more or less have addressed the breadth of questions that set forth by the conveners, and then I have a couple of interesting bits of the data analysis and planning process that I want to get into. But so first of all, one of the things that we have spent quite a bit of time is optimizing the scan strategy so that we could go forth with forecasting and also optimize things. And in the S4 meetings, it became apparent that the current available scanning strategies didn't serve all of our science goals, especially the transient science was suffering quite a bit with the tiled strategies where you observe a narrow field of the sky at a time and then move on to another narrow field of the sky, and only the totality of those fields will form a large area survey. And to address that issue, we came up with this high cadence strategy, where the strategy is such that you park your telescope at a certain observing elevation, and you observe as wide as you possibly can, and you let the sky do the drifting. So this obviously only applies to the Chilean observations. And the only reason for you to break such scanning is when the sun moves too close to the bore side of the telescope. Then you have to switch between rising and setting scans so that you don't end up with the sky with the sun in your field of view. And these illustrations here show the daily hit maps that you achieve with this high cadence scanning strategy. And the big hole in the middle is where the sun is and where you can't point the telescope at. And the only motion here is from, or the gaps in this particular example also include lunar avoidance. So we don't scan near the moon or the sun, and that's why you, at some times of the year, you will have one hole where the two are on top of each other, and at some points of the year, you'll have two holes where the sun and the moon are at different locations of the sky. But this strategy maximizes the cadence. Every every pixel of the sky that can be observed, because it's not obscured by either of the solar system objects, allows you daily cadence. And also there is a modulation that we can attach on top of this scan strategy that has the telescope scanning slightly faster when it approaches these turnarounds. That achieves a uniform integration depth across the entire sky, which then goes into serving our other major science goal for this this telescope, which is the N effective. We have discovered through the forecasting that a uniform field depth is one of the most critical figures of merit to optimize for achieving the science targets. I won't go into detail about the observation matrix because Colin did such a great job in describing it, but we have tools to build these for S4 and for the South Pole observations. And it really is just a sparse matrix that maps input sky pixels into output sky pixels. And the sparsity is the key here because it allows us rapid computation and rapid application of these matrices. And here's an example of the matrix actually in effect. This is the input map that we produce with the CMB dipole causing this large gradient. And if you just sampled the sky with your instrument with the simulated scanning strategy and map the data, you would still have the dipole in there. Instead, if you apply time domain filtering like the Bicep-Geck analysis includes, you reject those large scale modes, but you actually do the rejection along the scanning trajectory and nothing happens expressly in the cross scan direction. And the observation matrix produces exactly the same map without any time domain operations. It is just a multiplication of the input sky map and the matrix, showing how it could be incorporated also in Cosmoglobe style analysis. I had here a video. I'm not sure how well it presents you, but we have tools for simulating atmospheric noise, which are very useful in developing data reduction pipelines. In this case, it is a polar bear focal plane observing across a field of sky, where different angular scales are the same atmosphere at different distances from the telescope, moving with respect to one another and producing these very correlated noise fluctuations seen across the focal plane in the different detectors, presenting a major data analysis challenge because correlated noise is a lot more difficult to treat than uncorrelated noise. The data set could be visualized here as I've plotted on the right. We ran a 10-day simulation of noise, atmosphere, and signal across all of the proposed CMB-S4 telescopes, bands, and sites, and plotted the achieved polarization amplitude of these fields scaled to a full 7-year mission. And this is sort of the data set released to a project like Cosmoglobe for doing the component separation, and at least all of the sat maps will be accompanied with the observation matrix, For the lat maps, high resolution implies a lot more pixels, and certainly for the Chilean lat maps here at the final column, the data product describing those data could be a stack of simulations or some approximate isotropic descriptor. I won't have time to go into this detail, but you can ask me later if you like. It's a really fun exercise, combining our expertise from the South Pole and Chile for high resolution data reduction. And with that, I'll just summarize that S4 is a ground experiment, but it's being run like a satellite mission, and it needs to be run like that. We're relying on the high technical readiness level of these stage 3 experiments, and the planned survey won't start until 2031. Presently, we're at the stage of preparing our preliminary baseline design for agency review, and so there'll be plenty of more reviews and refinements of the design as things go forward. And everyone is invited to attend the next collaboration meeting held remotely in early August. Our summer meetings are focused on the science side. So I'm sure everyone attending this conference will have something to say. And that's it.